Across the world, hospitals are facing two critical challenges that directly impact patient safety and the workload of medical staff. First, nurses are required to walk back and forth between the pharmacy and patient rooms multiple times a day just to deliver medicines. This repetitive routine leads to fatigue, increases stress levels, and raises the chances of delivery errors, especially during peak hours. Second, patient rooms can continue to harbor infectious pathogens long after a patient has left. Manual cleaning is not only time-consuming and inconsistent, but it also exposes cleaning staff to harmful microorganisms, putting their safety at risk. Introducing MediBot, a fully autonomous, safe, and reliable robotic solution designed specifically for hospital environments. Let me walk you through how we built MediBot from scratch. We began by installing 4 geared motors, each fitted with omnidirectional wheels. These wheels give MediBot full 360-degree maneuverability, allowing it to move smoothly in any direction without needing to turn. Next, we mounted a high-capacity LiPo battery to power all 4 motors reliably. To give MediBot a voice, we added a text-to-speech module that enables it to speak status updates and interact with people around it. On top of the base assembly, we added another acrylic layer to hold the core electronics, including the motor driver boards and the servo motor fitted with custom 3D printed blades. Above this, we mounted the ESP32 DevKit V1, the controller responsible for driving all 4 motors and receiving commands from ROS2. We then installed a second ESP32 DevKit V1, known as Board B, which acts as the master controller. This board manages the UV countdown timer and sends instructions to the ESP32C6 slave controller for activating both the servo mechanism and the UV LED. The ESP32C6, acting as the slave board, was connected to the master using jumper wires. We also mounted the TM1637 4-digit display, which provides a clear countdown during the UV disinfection process. This slave controller handles the onboard RGB LED and operates the servo motor responsible for the medicine drop mechanism. Finally, we placed the camera above the robot for marker detection, enabling highly accurate autonomous navigation under ROS2. With the hardware complete, we integrated all micro-ROS communication between the boards, allowing the robot to execute complex, multi-stage tasks with seamless coordination. Now, let me demonstrate MediBot performing its tasks exactly as it would inside a real hospital. Upon receiving a medicine delivery mission from the nurse station, MediBot wakes up and navigates autonomously using markers and ROS2 navigation to the pharmacy, where after the staff places the medicine onto its tray, it immediately proceeds toward room 1, delivers the medicine using its servo-driven drop mechanism while announcing "Please collect the medicine," then, upon receiving a separate instruction for UV disinfection, moves to room 2 to perform a fully automated 10-second UV sterilization cycle with voice prompts disinfectant on and disinfection off, and finally, once all tasks are complete, returns to its charging dock, aligns, docks, and waits for the next instruction. MediBot delivers medicines, disinfects rooms, and returns to charge fully autonomously. It reduces workload, improves safety, and brings intelligent automation to modern hospitals. This is our first step toward healthcare robotics of the future.